Now that we have developed a model for the MOSFET, a pretty simple model, let's look at some of the non-idealities that will be of some interest to us as we look at design. So as I mentioned in the previous video, the square law model is not sufficient to assess the impact of the device characteristics on circuit performance. So we'll look at a few additional concepts in this video. We'll primarily look at subthreshold conduction, a little bit on body effect, and the effect of temperature on the VT of the transistor. So what is subthreshold conduction? So as the word suggests, this is basically related to what is the current flowing in the transistor when the transistor is biased below VT, or when the gate voltage is below the VT of the transistor. In our previous model, we assumed that no carriers are present below VT and therefore the current is zero. But as we looked at in the MOSFET and in reality the inversion layer does not switch on. There is a small inversion charge that continues to build up. Eventually around VT the inversion charge density becomes much higher than the whole density, and hence we call it VT. But please remember that minority carriers are present in the substrate even when VG is less than VT. And it is these carriers that can conduct a current between drain and source even when the gate is below VT. Now below VT, what we know is that the carrier concentration follows an exponential relationship with phi s. Right? And so the current we expect it to be exponential. That is, as you increase VG from 0, you expect the current to rise up exponentially. So therefore, when we talk about subthreshold, we normally consider a semilog IV plot because we expect the I to change very rapidly with respect to VGS. So now let's look at a very simple model for subthreshold conduction. So again, let's pull up a familiar NMOS transistor. It has a P substrate, N plus source, N plus drain. There is a VGS that is applied. Now in this case we are applying a VGS less than VT, right? So we expect that there is some inversion charge, but the complete inversion channel has not been formed. We also apply a VDS between the drain and source, right? When you apply a large VDS, now remember in this case, because there is no electron channel present between the drain and source, a large part of the VDS essentially falls across this reverse bias junction. And so we expect this lateral field here to be very, very small. And why is that important? That is important because that tells you that the current, these electrons that are going to be moving from source to drain, are actually not moving under the influence of the electric field, but rather because of the concentration gradient that is set up between source and drain. Right? And so the key difference between subthreshold conduction and post-VT conduction is that the current at subthreshold is because of diffusion of electrons from source to drain. Right? So when there is a concentration gradient set up in the channel, then I can talk about a electron current density which is proportional to the slope of the electronic concentration. Now, since this current is a constant at a given Vg and Vd, we expect this component, which is the slope, to be a constant, and so I can write my current density as Q times the diffusion constant times the average slope of the charge density, which is the density of electrons at the drain minus the density of electrons at the slope divided by L. Now if I assume that the surface has some potential phi s, remember that if phi s is the potential at the source end of the channel, right? So phi s is the surface potential at the source end. Now between the source and drain, there is a potential difference of VDS. So therefore the surface at the drain side will have a surface potential of phi s minus VDS. So therefore the electron concentration at the source for any given phi s is just given by Ni e power q phi s by kT, whereas on the drain side it is going to be this concentration at the source reduced by the impact of VDS. And therefore we can write the current density in subthreshold to be QNI dN upon L e power Q phi s by kT into 1 minus e power minus Q VDS by kT. So which means that if I can somehow figure out how to express phi s as a function of Vg, then essentially I've solved the IDVG characteristics. And this can be done based on what we learned in the modeling of the MOS capacitor. So a couple of things to point out in this conduction. One thing you see is that this conduction is inversely proportional to the length. So as you make your channel length smaller and smaller, you expect this leakage current to go up. Second thing is, you see it is weakly dependent on VDS. So this is again for a long channel MOSFET. For a VDS greater than a few kT by Q, this current basically is independent of the drain to source voltage. And it's a strong function of Ni. Now please remember that Ni is a strong function of temperature. Therefore this current is a very, very strong function of temperature. Now let's talk about characterization. Right. So when we want to characterize how the transistor looks like in subthreshold, we do by what is known as the subthreshold slope, right? And subthreshold slope is nothing but the first derivative of VGS with respect to VDS. And it is sometimes measured in millivolt per decade. That means how many volts at the gate are required to increase the current by 1 order of magnitude. Remember that current is going to keep increasing as you increase the gate voltage, because as you increase the gate voltage, you're inducing more charge, inversion charge in the channel, so you expect the current to go up. Now the subthreshold slope is measuring how many millivolts are required if you want to change the subthreshold current by an order of magnitude. Let's try and see if we can arrive at a conceptual expression for the subthreshold slope. So at any surface potential phi is 0, I can talk about a diffusion charge density JD that is given at some Vg or some phi s. So if I want to find what is the current for some small change in this surface potential, that can be essentially written as JD of phi s 0 plus delta phi s, which is nothing but the JD at phi s 0 times e power q delta phi s by kT. So the increase is going to be through the exponent. Now let's look along the gate. Remember, we want VGS by IDS. So this is giving you IDS by phi s. Let's try and see if we can connect delta phi s to delta VG. So if we look along the gate, right? Along the gate, I know that if I wiggle VG, so at any point of time, VG is going to be equal to Vox plus phi s, right? Let's assume VFB is 0 in this case, which means that when I apply VG, some part of it is going to drop across the oxide and some part of it is going to drop in the semiconductor. So if this VG increases slightly, some of the increase is going to be taken by the oxide and some of the increase is going to be taken by the semiconductor side. Therefore, I can write delta VGS, some delta Vox plus some delta phi s, right? It's this capacitive division. That's why not all of the VG change reflects in the semiconductor, because some of it has to drop across the oxide. And if I recollect the terms, if I want to express it in terms of the capacitances, basically my delta VG can be written as CS by Cox plus 1 into delta phi s. Right? So if I now want to write how the current density changes as a function of a small change in the voltage, it is essentially given by the current density at that Vg voltage exponentially changed by this delta Vg by 1 plus Cs by Cox, because this is the effective change in the surface potential, and it is that change in the surface potential that changes the minority carrier density in the transistor. So therefore, to change JD by 1 decade, I essentially that the voltage required is going to be S. So I set that to be equal to ln 10, and that gives you this very famous relationship that the subthreshold slope is given by 1 plus Cs by Cox times 60 millivolt per decade at room temperature. So this is typically how the IDS versus VGS looks like. It is exponential. So remember, I'm plotting log versus linear. So in the semilog, this is the straight line and this is the slope of the graph we're after. Now if again I design a very good transistor, if I design a very good transistor such that my CS is much less than Cox, then S is 60 millivolt per decade. So this 60 millivolt per decade is an important number to keep in mind. This dictates what is the fastest transition you can get in a MOS system. So you will have to spend at least 60 millivolts every time you want to change the current by 1 decade. Normal transistors or real transistors are always going to have something slightly larger than 60. So 60 is the best you can do. Now, obviously, this is a very hand-wavy, simple model, but it gives you kind of the understanding of what process parameters or what device parameters can influence the subthreshold slope. You can do a more accurate analysis by looking at the charge distribution and the current density over the entire region of the depletion. So here we just assumed it at the surface. In reality, you're going to have current flowing across the entire source drain region, right? What I mean to say is that in the transistor, we have essentially just we blocked it up as one current just at the surface. In reality, there's going to be some current in this along the entire junction depth of the source. And so that needs to be accounted for. And if you account for that, you get an expression which obviously is more complicated than this, but has the same kind of relationship. You still get the 1 plus CS by Cox times KT by Q ln 10. Right? So 60 millivolt per decade is kind of the limit, or it's kind of the fastest you can switch the transistor. So therefore, if I want to use a MOSFET as a switch, that is, we want it to have two stable states, one which is a low leakage state and one which is a very high conductive state. We want the subthreshold slope to be as steep as possible. And what are the ways to do that? One way obviously is to reduce the TOX or increase the oxide capacitance. The other way is to reduce CS, which means reduce the doping concentration. And the third is to decrease KT by Q or reduce the operating temperature of the CMOS or the MOSFET, right? And so if you operate the MOSFET at much lower temperatures than room temperature, you're going to see better switching characteristics. Now this subthreshold slope therefore imposes a limit on how low a VT you can get, right? And this VT, we'll see later, has a profound impact on the noise margins, on the performance of any digital system. And so it presents a fundamental limit. So subthreshold slope, the 60 millivolt per decade, is a fundamental limit of the MOS structure. No amount of engineering with a kind of a MOS structure can fix this. Obviously, there are other devices which have been worked, which are available, like the IMOS, like the TFET, etc., which have shown that you can get switching characteristics faster than subthreshold, but they are not MOSFETs. They are devices based off MOSFETs. The other topic we want to think about is the body effect. So far when we've looked at the transistor, we have looked at the case where the source and the substrate were both at 0 volts. Now what will happen? Suppose instead of this substrate being at 0, I apply a negative voltage at the substrate. So if I apply a negative voltage at the substrate, essentially for the same gate voltage, I have increased the depletion region width, right? And so therefore what happens is, to first order, this would seem like it should make it easier for us to invert the channel, or in other words, by applying this voltage or applying the voltage at the substrate with respect to the source should change the VT of the transistor. If we invoke the chart sheet model at any point V in the channel, the chart sheet model gives us that Qi is equal to Cox times the net Vox. Now remember that because of the fact that you applied a bias between the substrate and the source, the total charge in the capacitor increases, and so the total inversion charge density increases, from which you can extract the current, again using techniques we had used in the MOSFET lecture. And what we see is that if you now approximate this to low VDS, you get that device looks like the same device only with a changed VT. So essentially what happens is that by applying this source to substrate bias, you can play around with the VT of the device. So in many of the older technologies, this was used to actively modulate the VT. For example, by changing the VT, I can change the on current and the off current. So if I'm able to actively change the VT of the device by applying a bias, then I can make the same device appear faster or appear slower. And this was a very common technique used to speed up block performance in digital design. Last thing I want to talk about is the temperature dependence. So we know that in semiconductors, semiconductor performance is a very, very strong function of the temperature. And therefore it is very critical that whenever you design a new device, whenever you design a circuit block, it's important to characterize its performance over the expected range of temperature. So statistics indicate that as temperature increases, your Ni goes up and your Eg goes down, which means that it is easier for the MOSFET to be inverted at higher temperatures, or in other words, the VT of the transistor reduces. So in general, we see that there is a weak function of VT as a function of temperature, and the VT of the transistor reduces as you increase the temperature of the device. What happens to transistor performance is something we look at when we look at digital circuits. So there are a lot of non-idealities in the MOSFET. Obviously, not all of them are modeled here. I've picked a few which can be thought of as extensions to the traditional model. But please remember that there are many, many more than these. In modern MOSFETs, as I've mentioned time and again, the square law model is grossly insufficient. And so normally when you work in this field, transistor models are developed from extensive silicon data, and they have a lot of parameters, and many of them are empirical. What I mean by empirical is they are not necessarily physics based, but rather they are based off experimental data. And there is always, when we do modeling, there is a trade-off between how predictable you want the model to be to how easy or how quick it is to simulate or implement. One thing to note about is, even though we've discussed a lot of device physics, and physics-based models give us a lot of intuition as to how the device works and how to plan for subsequent devices, they don't tend to be very accurate when we actually want to build circuit models. So once we think about making a chip and sending it to the foundry, physics-based models tend to be inaccurate, and we tend to rely more upon our empirical models just because their predictability is much better. But there is a value for the physics-based model because it helps us understand how the device works, and it also helps us use these models to predict how transistor performance will look like as you scale technology.